recording to actually start. The light probably... Oh, it's already started. Okay. Hello, I'm David, and now you know what I look like. You don't have to see me again. Okay. I'm the coordinator of the Maths Learning Centre, and for those of you watching online, this is a revision seminar in semester 2, 2019 for Applications of Quantitative Methods in Finance, a course with a whole lot of more or less random stuff. Some of it literally random because it's got probability in it. First maths dad joke of the day. So I've been given some requests and I don't know if I'll get through them all. I'm going to start with implicit differentiation. So, right, let me just talk about how I understand the general idea, and then I can do an example. That light is awful, isn't it? Let's just, that's a bit better. Okay, so, right. You just think. All right. So there's a big idea in maths, which is that, and a hope really, that any shape that I might draw, a curve, you would expect to have some sort of equation that describes that curve. And when I say equation, I mean something involving x and y equals number. X and y's equals number, something like that, all right? And the hope is that we do know that every possible equation like that does produce some sort of curve. Some of them are wickedly strange, and the hope is that any curve has one. But there's an issue with that, is that it's much easier for us to think about things on this xy plane when they are written as this. This has an equation like this, but we would prefer something more like this. Y equals something in terms of x's. And the reason we prefer that is that we can do things like derivatives and given a particular x, it's easy to figure out what the y is that goes with it, and that's great. But the problem is that this one doesn't match this, because this formula only has one y for every x, whereas this function has 4 y's for this x, which is an issue. Okay? We would prefer this, but most curves are not graphs of functions like this. So that's an issue. All right, let me just draw something. I'm just going to show you something. You wouldn't be able to use this in an exam because, of course, you won't have a computer that accesses the internet in the exam. I'm sure they won't like that. But just let me show you. Desmos is an online graphing calculator, and it can say all sorts of things. Any equation you could type there will produce something, and it will be curve-shaped when you do it. And this one's pretty funky. If I zoom out a bit, it goes on sort of outwards forever in this direction, and it sort of stops here. But some of them are really quite bizarre. You know, some of them are not that bad, they're pretty nice, and some of them are weirder. Okay. So the issue is that if we are on this, sometimes we do want to know what the slope is at a particular spot. But because this graph is made of, you know, at least two different pieces that could be y equals something, that's a problem. Okay, so what we would like, I'm just going to redraw our picture. What we would like is if we are at a specific spot, we might like to know what the tangent is there. And the idea of a tangent, sorry. If we were at a specific spot on my curve, then we might like to know what the tangent is there. And the idea of a tangent is not so much to have this whole line, but just to have a little piece that matches up to my curve when I'm really close to it. So if I go back to the Desmos, if I zoom in on this bit, if I go close enough, it looks straight. And that's what I'm trying to get at. I'm going to try and get at the idea that if I'm really close to the point I'm interested in, I can approximate this curve by moving along a straight line. And that straight line is the tangent. And some places, like just here, if I go in far enough, it's almost flat. And that would be a minimum at that spot. Okay. Zoom back out again. But this is the useful thing. If I zoom in far enough, the rest of the graph I can't see it. So I might have a chance of making just this bit as y equals something x. And so that's the idea. What I'm going to do is I'm going to zoom in here with my magnifying glass. And in just this part here, I can write just this bit as y equals function of x. And then that, if I differentiate that function, then I can figure out the slope. Yep. Oh, crap. Thank you. I'll get used to it again. Each new lecture theatre I have to remember. This one's a lot further away from the document camera. So if I zoom in with the magnifying glass on this bit here, look inside my magnifying glass, and that's the point I'm at. And I can just write just this part as y equals x, y equals some function of x. And I can find the slope of that. So the slope here will be dy on dx, because that's what a slope, you know, it's the derivative. Okay, so that's great. But the really nice thing is that we don't actually have to figure out what this function actually is in order to do the derivative. We just have to know that it's possible to find it. And at every point on the curve, it's possible to find it. It might be a different function at different places, but every point on the curve it's possible. And one thing we do know for certain about the points on the curve is they satisfy the equation of the original curve, like the original equation. So now I'm going to do an example. Just give me a second to set it up. You don't need to see what I'm doing here. I'm deliberately not showing you what I'm doing. Okay. Okay, so I'm going to do roughly the curve that I drew. But I'm just going to change what number it is, if that's okay. All right. So, well, that's supposed to be a minus there. Really hard to write when you're looking at a different screen. So what I'm going to do is I'm going to attempt to find where this, the tangent to this curve at a point. So we're going to find do they get you to find the equation of the tangent or just the slope in their things? You don't know? At the point 1, 2. So the first thing we should do is check that the point 1, 2 is actually on this curve, because if it's not, then the whole question is stupid and doesn't make any sense. You can only find I mean, you can technically draw tangents from that point over to the curve, but you haven't been taught how to do that, so it'd be useful to know. So let's see, 1 cubed is 1, minus 1 times 2 is negative 1, plus 2 squared, so negative 1 plus 4 is 3. And 1 minus 2 is negative 1 squared, and 3 plus 1 squared is 4. Okay, it does work. When I sub this into there, it really is on the curve. So I'm just going to check something. One, 2. And so we have 1 cubed minus 1 times 2 plus 2 squared plus 1 minus 2 squared is indeed 4. So yes, 1, 2 is on the curve, which is the whole point of this equation. If you sub things in, you can tell whether they're on there or not. So if it didn't come out to 4, it wouldn't have been on the curve, and I would have said, this point is not on that curve, I can't answer the question. Which has happened at least once in an exam that I've been in, that the question wasn't possible. So sometimes people who check these things miss that sort of thing. So the slope of the tangent at that point, excuse me, I know that y is secretly a function of x. So in my head I'm thinking, what I'm thinking is that y is some function of x. There is some wicked formula involving x that I can sub in that nearby to this point, nearby to 1, 2, this is what happens. So that's what I'm thinking. So all the time I'm thinking that every one of those y's is really some sort of function, some sort of formula involving x. Okay, so when I do the derivative, it's going to need to involve imagining that there's a function there. So now I need to keep track of both of them, so let me just copy this here. You won't need it, I just need it so I can see them both so that you can see them both at the same time. Okay. Right, now we can see them both at the same, see what I'm doing and the original equation. So I'm going to differentiate this, and knowing that y is really a function of x. So if I want to do it properly, the official working is you start like this, most people. So the symbol d on dx stands for the derivative of. It doesn't just mean the derivative. It doesn't make any sense without something next to it. So you can't just write d on dx equals, for example, because it's not a thing that can be equal to something. So I'm saying the derivative of this must be the derivative of that, because what I've done is the derivative for both of them. And I can do this one. 4 doesn't change when x changes. It's always 4 when you're on this curve, and so it's 0. Okay, so this thing, do you know what? I'm probably going to take quite a bit of space to do this. It might take 2 lines to draw this, so I'm just going to put it down there if that's okay. Okay, so the derivative of x cubed I can do. The power comes down, and then the power goes down by 1. That's great. This next bit, I might even colour code each piece so that you can see what's going on. Okay, this next bit here is 2 things multiplied together, and the y is really a function of x secretly. And so this is something involving x multiplied by something else involving x, so it's a product rule. So I'm going to have to use the product rule for this. So the derivative of minus x, well, I'm just going to put a minus and do all of it. Okay. So the derivative of x is 1, and then I'll keep the y, and then I'll keep the x, and I'll do the derivative of y. And the derivative of y is dy on dx. So that's how I did that. How are you feeling about that? Okay, and so the next bit there, I'm just going to put it on the next line if that's okay. All right, it'll be minus something. So now this is really a function inside a square. Like it's really this, right? Thing squared, and there's a function here. So I have to use the chain rule to do that. So if I did it, I'd differentiate the outside, which would be 2y. But then I have to differentiate the inside, and the inside was y. So that one was done with the chain rule. And then again, I have to use the chain rule again. So I've got one more colour. So I'll get 2x minus y, and that's the derivative of the outside. And the inside, the derivative of x is 1, and the derivative of y is dy on dx. And so that's what I've got. So that's how I do implicit differentiation. Of course, it's not finished yet because I haven't actually got what the slope is at the point I'm interested in. So what I can do is the slope at the point I'm interested in is dy on dx. I'm imagining that there is a function, y is equal to a function of x, and I'm differentiating it to get dy on dx, and that should tell me what the slope is. So I'm going to get a formula for dy on dx, which means I'm going to have to do some algebra on this to get to where I'm going. So let's see. 3x squared. Just going to expand it out. So that minus belongs to both of these. That's beautiful. That one, yeah, I'm going to expand it. I might keep the 2x minus y together if that's okay. So I'm going to call that 2x minus y. So that's this times the 1 minus 2x minus y dy on dx equals 0. Running out of space. Should have given myself more space, but anyway. So each thing has been just dealt with. This thing here has been expanded out. That 2x minus y has been multiplied by both of these things. I only want to expand it out far enough so that the dy on dx's are free from being inside brackets. So now I can see that these bits have a dy on dx and the other bits don't. Yep. Do you want me to talk about something? Because it's your revision seminar, you're not slowing me down. Okay, cool. All right. So all of these dy on dx's are here. I would prefer, my goal is to get dy on dx equals. And so what I'll do is I'll remove everything that doesn't involve a dy on dx and remove it from this side. So the 3x squared doesn't involve a dy on dx, so I'll put it over this side, and by that time it will be a minus. So I'm going to subtract this from both sides, which will end up with this. Yes?
Sorry, Centra. 2 times x minus y,
Mm-hmm.
and then after that it's negative 2x minus y dy by dx.
Mm-hmm.
So wouldn't it just be positive 2 and then negative dy by dx?
Positive. Where's the positive 2?
Yeah, over there, yeah. So is that, how did you get that?
How did I get this?
Yeah.
I have run out of colours. Oh, green. No, that's good. Light green. So this thing got multiplied by both of those. But I didn't expand it any further than that. I just left it like that because I couldn't be bothered doing any more. So you're right, I could have done x times 1 and x times minus dy and dx and minus y times 1 and minus y times dy and dx. I could have done that, and that would have been fine as well. I just decided I didn't care, and I made my work just a little simpler. Okay, so this bit doesn't involve dy and dx, so I'm going to remove it from this side of the equation and put it over here, which means it'll be minus, because I'm really subtracting that from both sides. That doesn't involve a dy and dx, so I'll add it to both sides so that it's gone from here. This does involve a dy and dx, so I'll leave that here. This does involve a dy and dx, so I'll leave that here as well. And this doesn't, and so I'll move that out the way. And this does, so I'll leave that here. Or just room to fit it in. I will give myself ones that are complicated. Sometimes you need one that's complicated, otherwise you don't see all the things that happen. So, okay. So now all of these things here, and here, they all have a dy and dx in them. And so if I factorise that, then there'll only be one dy and dx written on the page. Okay. At this stage, it's probably worthwhile expanding this out now, I think, because I can see that I can have this minus x will combine with the minus 2x. So I might do that now. Oh, sweet. Okay, I've just expanded out this bracket, and look at that, a minus 2y and a plus 2y. Sweet. That's beautiful. And so now I get that dy on dx is minus 3x squared plus 3y minus 2x, all divided by minus 3x. Because this thing was multiplied on, so I can divide by it. Okay. It freaks me out a little for the denominator to have a minus in it, like that. So I might multiply the top and the bottom by -1, just to get a final formula that is a bit prettier. There we go. Yep. It is 3y. Good noticing. I really wish I had a mistake fairy in my exam to notice these things for me, because this is the thing that would always lose me marks. I would copy a 3 and it would be a 2, and copy a minus and it would be a plus. So it's the thing that I always go back looking for to compare each line to the one above. So thank you very much. Okay, so here we are. We have now found a formula for what dy and dx is. So this formula should allow me to calculate the slope of any point on this curve, as long as this denominator isn't 0. So okay, and so I should get that at the point, what was it, 1, 2? dy and dx is 3 times 1 squared minus 3 times 2 plus 2 times 1 over 3 times 1. Which is 3 minus 6 plus 2 over 3. So 3 minus 6 would be -3 plus 2 would be -1. We get -1/3. Okay. Couldn't do the next bit I'm about to do in the exam, but I can do it now to help myself feel like make myself feel like I'm doing the right thing. And it is not looking like what I think it should. I feel like I made a mistake. So there's the 0.12. It looks to me, like the slope is positive at that spot, not negative. Cursors. All right. Well, the first thing I'll check is that I wrote the same thing on this as I did. And it's different because, have you noticed, have you noticed, I wrote a minus here, and the original equation had a plus. Oh, classic me. All right, so in order to save this, I'm going to change the original question, which you can't do in an exam. That would be pleasant. So I don't like your question. I'm going to do this one instead. Crap, and that won't be 4 anymore, will it? So I decide to change it to, just a second. It's -4. Sweet. Okay. So if I was in an exam, my only choice would be to go back and do the whole thing again, or possibly change my minus signs and see if I could track what was going on. Or if I ran out of time, I could say, sorry, I've just noticed it's different to the original, but I didn't have time to fix it. And they will still look to see if you did the right thing and give you some of the marks. So it's always good. But I'm just going to go look at the actual picture now. Okay, so on the computer, this is what the curve actually looks like. And when I zoom in on the 0.12, the slope is indeed negative. It's going down. And it's, if I'm very close, it is going down approximately, it's going, for every one across, it is going down about a third. Because to go across 3, it goes down 1. So the slope is negative a third. So good, our algebra is right. How would you check it in the actual exam? It's a bit hard, but what you could do is a useful thing you could do if you really wanted to check it is that you could say, you could actually move the x a little bit and figure out what y goes with it. But again, you'd actually have to solve that equation, and we don't like that. Yeah, it's not very easy to do, to check this sort of thing. Yeah, sadly. Can't even tell how to make sure that it's going to come out to be negative to even check that. So I don't have a good strategy for checking this other than going through every line and making sure that the minuses match from one line to the next. Okay, cool. So the only other piece of information that we might want to do is we might want to see if there are any places where the tangent is vertical. So, follow up. So the tangent will be vertical when this slope doesn't exist, because the only lines that don't have an actual slope are the vertical lines. And so I will not be able to calculate what this is if x is 0. Now, if both the top and the bottom is 0, it's a bit tricky to know what is going on at that spot. But if the bottom is 0, you definitely do not get a usual slope, so it won't be any line other than a vertical one if it exists at all. And so I know that there is I know that dy on dx is undefined when the denominator is 0. So when 3x is 0, which means x is 0. And if x is 0, we can figure out what y is by subbing it back into the original formula. And so we get that the original formula was x cubed minus xy minus y squared plus x minus y squared. And so we get 0 cubed minus 0 times y plus minus y squared plus 0 minus y squared. So negative 4, isn't it? Equals negative 4. And so we get y minus y squared plus y squared equals negative 4. So 0 is negative 4, so there's no solutions. So no, there are no points where it has a vertical tangent, because the only place that can happen is when x is 0, and if x is 0, there's no solution for y. Okay, so therefore, no points with a vertical tangent. So if you had gotten solutions for y, then they would have given you coordinates for where the vertical tangent is. And I just want to check it on my picture. X has to be 0 to get a vertical tangent. This graph doesn't meet the x-axis, doesn't meet the y-axis is when x is 0. This graph does not meet the y-axis at all. So there are no vertical tangents. Not perfectly vertical. I mean, if I went up here, it's pretty close, but it's never quite vertical. Not quite. Yeah. Cool. I like this graph. All right. I think that'll do. So it's good that actually we came up with one that didn't have any, because I don't think you've seen an example of that in the course. So I kind of like that. So there's two ways to not get a vertical tangent. One is that the denominator is never 0, and the other one is that it is 0 sometimes, but none of those points are actually on the curve. Okay, I like it. So any other questions or thoughts about that? Because it would be nice to just make sure that we covered everything that people want to know about this. Okay, cool. That was good. So that's our first one. It took me, it was a while, I was teaching implicit differentiation, and it was a while before I realised what was happening with that little equation that's nearby. Yeah. Okay, so we did that. That's good. So, what do you reckon out of these things? There's what, 5 things there-ish? That's 5 things. Okay. So, I'm just thinking about some stuff. If you had to choose between Lagrange multipliers and DEs, what would you choose? So stick your hand up if you had to choose, stick your hand up if you would choose Lagrange multipliers for me to talk about. All right, differential equations. We've got 2 people committing. Okay, as opposed to 1. So we'll talk about that. We may still talk about the other one. It would be useful to know what your lecturer says about differential equations. Is that in this same book? But there's a thing there, it says separable when someone asked about that. I'll pop this down. So who wrote this? You? Yep. You got any? I mean, it says separable, so obviously we have to talk about that. Is there anything in particular you want to know? Nothing in particular? All right, cool.
Would it be under 2 variable?
Differential equations is not a 2 variable thing as far as I know.
I'm pretty sure we did it recently.
If you've got the bit of the notes, that'd be useful because I want to know what your lecturer says about it, because they do differential equations in about 6 different first-year courses and they all do it slightly differently. So, yeah. So doing in Mathematics 1M and Mathematics 1B and AQMF and yeah, several. Hey, have they put on a peer-assisted study session for this week? No? A pass class? No, that's all right. Just checking.
It's on Tuesday, the exam.
No, yeah. It's all right. Oh, cool. Thank you. Okay, so I would have to be after integrals, I guess. So I'm just having a quick flick through the notes. Do you mind if this is seen on the screen? You don't? Okay. So this is differential equations. That's what they are. That's separable. Yeah, it's all right. Separable. Oh, and then that's the end. Okay, cool. All right. All right, I know what I'm doing now. Some people just shorten this to DEs, in case you want to know. Okay. So in most of the rest of algebra, the unknown is a number. And you've got like an equation involving x and or y, and you try and figure out what the x is that makes the equation work. That's what most of the rest of algebra is. We did it just before, you know, which x makes this 0? But in differential equations, the unknown isn't a number, it's a function. And our goal is to figure out what the formula for that function is. So in a differential equation, information about a function and its derivative is used to figure out a formula for the function. Okay? That's the big idea. The goal is to find a formula for the function. So if you have something involving x and y, and dy on dx, then the fact that you have dy on dx is telling you that y is a function of x, and the goal is to find y as a function of x. If you have something using a p and a q, and you've got p on dq, then your goal is to write p as a formula involving q. That's the idea. So if you see an equation with like y and x and dy on dx equals whatever, it doesn't really matter, an equation with all that stuff in it, then that means the goal is to get y equals something involving x. I know that's a really weird thing to write, but it's hard to write it down because in my head it's it's just a vague picture. Okay? And so whatever it has d thing on d thing means that you want this as a function of that. That's the goal. Okay. Right. And that's a useful thing to keep in your head. When they say solve this differential equation, they mean find y as a formula in terms of x, or whatever the variables actually are. Okay. So as far as I can see in the notes, you have basically 3 methods of solving, one method of not solving a differential equation and 2 methods of solving them. Okay? So you have a method for checking if a solution is correct, and you have a method for 2 methods for actually solving them in these notes. So that's what we have in here. So we have method for checking, and we have 2 methods for solving. Okay, and it's not really a method for checking, it's just the same as all methods we have for checking all sorts of things, which is to sub it in. So I'm going to talk about those. So first, checking. Now checking is what I call it, but a mathematician would call it verifying. Okay? A mathematician calls, so when the word verify means show the truth of, because it comes from the word verity, which means truth in Latin. Verify means make true. Okay, so if you were asked best to do it as an example, verify that just give me a second. Verify that give me a moment. Sorry, I'm going to rub something out. Just need to find my eraser. Okay, so verify that this equation, this formula, is a solution to this differential equation. Okay? And what we do is we sub it in. Sub is short for substitute. So what we need to do is we can replace this p with e to the 3t, and we can figure out what dp on dt is and put that there, and then figure out what this side comes out to, and if it comes out to 0, then it's a solution. That's the idea of this thing. So we can say, well, p is e to the 3t, and dp on dt is 3e to the 3t, because the derivative of e to the anything is the same, but then I'd have to multiply by the derivative of that because of the chain rule, so I get that. And so 2 dp on dt minus 6p is 2 lots of 3e to the 3t minus 6 lots of e to the 2 dp on dt minus 6p is 2 lots of 3e to the 3t minus 6 lots of e to the 3t, which is 6e to the 3t minus 6e to the 3t, which is 0. And so therefore, so yes, it is a solution, because it works. You'll note something interesting about the way that I've done this. I have figured out what this side is and revealed that it's 0 at the end. I haven't started by subbing it into the whole equation and then getting 0 equals 0. That's not actually a valid way of doing the mathematics, because it makes it sound like you've assumed it's true to begin with. So it's best to sub it into both sides of the equation, and then at the end you say, aha, they're equal. Yeah. So I'm going to do one more. It'll just take me a moment to figure out what I want to do. Okay, this is going to be my differential equation. Well, sorry, I'm going to write down a second. That's a bit distracting, guys. So maybe a bit quieter. Right. Verify that y equals x squared is a solution to that. dy on dx all squared is equal to 2 times d squared y on dx squared times y. Now, this is not a differential equation that you are expected to know how to figure out a solution to at all. But you can always check if something is a solution. Okay, this is a second order because it's got a second derivative in it, not because of the squared, but because of the second derivative. And it's not simple because this is squared. So you haven't actually been taught about any second order derivative differential equations at all. You've been told to recognize them. Okay, so I can always check, and I'll check. So I will figure out what these things are. dy on dx is 2x, and d squared y on dx squared is 2. Okay, so dy on dx squared is 2x squared, which is 4x squared. So what I've done is I've taken this part of the equation and I've done this. Some people would even tell the reader what they've done. They've said like the left-hand part of the equation. And now let me look at the right-hand part of the equation. So we have that 2 lots of d squared y on dx squared times y is 2 d squared y on dx squared is 2y is x squared, which is 4x squared. So they're both the same, so therefore the equation's true. So yes, it is a solution because both sides, both parts of the equation work out to the same answer. So equals, so yes, it is a solution. Because if it is a solution, this thing is equal to that thing, and it is true that this thing is equal to that thing because they are both 4x squared. Yep?
Do you think there'd be a time where we'd be given one and it doesn't work?
Well, they might say, decide if this is a solution. That's a reasonable thing that they could ask. So that you could say, they could say verify this is a solution. So you can't verify it if it's not true. But they could say the phrase decide if y equals x squared is a solution to this. And if these work out to be not equal, then it's not a solution. But that'd be totally something they could do. That's a very good question. And that's a great thing to be able to do when you're studying, to say, I can imagine a different kind of question. Is that reasonable and could I answer it? Always a good question to ask. Okay. All right. So that's not really solving differential equations. That's just checking if a solution that you've sort of thought of is correct. Okay. Now you have been given 2 other methods. One of them has a name and the other one does not have a name. So the first one that you were told doesn't have a name. And it goes with, oh no, ooh, we have technically got 3. Okay, we actually have 3 methods. Just give me a second. No, it's still only 2 because one of them I can wrap into the other one. Okay, it's all good. The world makes sense again. Okay, so the first method of solving doesn't have a name, but it goes with things like this, of this sort of shape. dy and dx is function of x. Okay? And we know how to do that because the whole point is that to get this formula I had to differentiate, so therefore to get the y back I have to integrate, because integration and differentiation are the opposite of each other. Okay? And what we'll do to do this is we'll just integrate. Alright, so for it as an example, it's always fun being next to the childcare centre. So, yelling. Though a couple of years ago in this lecture theatre we had a possum running around in the roof as well. So it was all very interesting. So here's an example. Of course, it doesn't have to be y and x. It could be any letters. Like that. Well, if the derivative is this, to figure out the original, I'll do the integral. So that means that y must be the integral of this. Yay! So I'll just integrate it. So the 2 will go up to 3 and I'll divide by the new power. And then this 3 will still be there because it's multiplied on. And then e to the x integrates to still be e to the x, and then there'll be a plus c on the end. And that's it. Let me do another one. This is going to be awful, but anyway. dA on dt is t e to the t plus 1, and a of 0 is 5. Because a is the name of a function, so you can sub in t equals 0 to get the answer 5. So this one's a little different to the other. It's similar because we have derivative equals formula involving t, but we also have this stuff, and there's a name for that. That's called an initial condition. The reason it's called an initial condition is because it tells you what happens when t equals 0. So if t was time, time equals 0 is the beginning, and initial means at the beginning. So that's why it's called an initial condition. So what you would do is you would integrate it. Okay. Oh, I'm going to have to do integration by parts. I did that deliberately just so I would cover it in the seminar. So we did integration by parts, didn't we? Good. Okay. So this bit doesn't need integration by parts. That one's going to be okay. So I'm just going to separate it into 2 separate integrals, if that's okay, just so that I can... Okay. So this bit here I'm going to have to do with integration by parts, and the way that integration by parts works is that you would call these, I will call them f and g if that's okay. And then when you integrate, one of them will have a dash at some point. It'll be like fg dashed or f dash g. Is that how your lecturer does it? U and V? Okay. Oh, you can use whatever letters you want. I will call them U and V because then that's more familiar. But basically the same idea, right? And one of them is U and the other one's V dashed. Or it's okay for me to have one of them as U dashed and the other one as V. It doesn't really matter as long as the opposite way round at the other end. So UV dt, it's like the product rule for integration. UV dt will still be UV, but it'll be minus UV dt afterwards, and I haven't done anything to the 1 dt. Okay, so what I want to do is I want to choose which one has the dash so that at this stage, when one of them will have a dash here, which means it's going to be differentiated, by the time it gets differentiated, it will go away. That's what I'd like. So if I differentiate the e to the t, nothing will happen, it'll still be there. And if I integrate that t, it's just going to get worse, it'll go up to t squared. But if I differentiate the t, it'll become 1. And a 1 times something, well, it's basically gone away. So I'm going to differentiate the t like that. But sometimes if they were written the other way around, I would do the dashes the other way around. That's how I think about it, that one has a dash and the other one doesn't. But some people prefer for the u to always be the one without the dash. And then you just write them in the opposite order and it'll be okay. Okay, so this is based on the idea that u is t, which means that u dashed is 1, and that v dashed is e to the t, which means that v is e to the t. Okay, that's the idea that I'm using. I don't do integration by parts often enough to be able to do it in my head. So I always have to write this down or I just get it wrong. So the u is t, the v is e to the t, the u dashed is 1, the v is still e to the t. Okay, and I reckon it's safe to do that final integral now. So the integral of e to the t is still e to the t, and the integral of 1 is t. Because that's, if I differentiated t, I would get 1. Okay, so that's what it is. So that's my formula for what A is. But I have one extra piece of information I haven't used yet. And so I will go that, all right, but A of 0 is 5. And A of 0 is actually 0 e to the 0 minus e to the 0 plus 0 plus c. Uh-oh, sorry. And this is 0 minus 1 plus c. And that's supposed to be equal to 5, which means the c must be 6, because I'll solve this equation. And so therefore, A is actually t e to the t minus e to the t plus t plus 6. All right, so those are the most simple kinds of differential equations. Not to say that they're simple per se, but they are the simplest out of the list we've got. And what we have to do to solve them is just integrate them. Yep? Yes, this is a particular solution. This is a general solution. Yep, so I'm going to write that in. This is a general solution. And this is a particular solution. The idea being that if you don't use that information that A of 0 is 5, then there are all these different equations that could work with all different C's. And so it's general because there's lots of different options. And this is a particular solution because it's just one option, which is what particular means. That is the sort of thing that I'm very grateful for with people in these courses. You know, mention things that I haven't mentioned that occur to you. That's useful stuff. Okay. So there's one more method that we have. Your lecturer mentioned it as two different methods, but it's really the same method. And it goes like this. We're going to do separable DEs. So a separable DE is one that where you can separate the two variables onto either side of the equation using multiplication and division, and or division. So the traditional description of it is this. A separable DE means that you can arrange it. You can arrange it to look like dy on dx or dp on dt or dA on dq or whatever. You can arrange it to look like the derivative of things is function of x times function of y. Or it doesn't really matter. Function of x divided by function of y, or the other way around, that'll work just as well. Hey. The other way around will work just as well. Could be this way as well, doesn't really matter. The idea is that the thing over here has to be made of two separate pieces, one with only x's and one with only y's, that are either multiplied or divided. And the reason you want that is because you want to be able to rearrange it to look like this. Using multiplication and division only. You're not allowed to use addition to do this. Only addition, multiplication and division to get something like this. Function of x dx. So we're going to, even though it's not technically correct, according to the rigorous definition of what differentiation means, it's not technically correct to see these two things as stuff that you can multiply and divide, but it's okay in most situations to separate them. I mean, over in your economics courses, they'll do it all the time. They're called differentials as opposed to derivatives. So anyway, so the idea, this is the big idea here, you want to rearrange it to get that. Something involving y's, dy, something involving x's, dx. Except I just want to say to you, it doesn't matter if this is just a constant or if this is just a constant. That's okay. It's just not allowed to involve x. And it's okay if this is a constant. Just no y's. Okay? Because technically, a constant is a function of x. Because if you have like y equals 2, then no matter what x is, you can still figure out what y is. It's 2. So a constant is still technically a function of x. But it's just worth pointing it out. So anything that you can arrange to do that is a separable differential equation, and the way to solve it is to arrange to do this. And you have seen several examples of them, and some of them may or may not have looked like it because the lecturer hadn't called them separable at the time. But we have the advantage of being in the future from that point, so we can see how they're similar when we couldn't see it before. So we don't have to keep them as separate in our head. We can just do them as separable. Okay, so best way to do this is to do some examples. So classic example is I'm going to just be really creative with my letters here. dm on du, just to be fun. Okay. dm on du is 3m. That's what I've got here. Okay. Oh, and let's just chuck in something. Yeah, let's do 0. Where m of 0 is 8. So we're going to solve that. Should really probably put a verb in here. Solve. Okay. So when you're asked to solve a differential equation, the goal is to write this variable as a function of this variable. And this is already written in the correct format. This is dm on du and something involving m times something that doesn't involve m. This will be the thing that is my function of x. So as long as I can rearrange it so all the m's are with the dm and all the u's, if there are any, are with the du, I'll be okay. So I can do this. So most people, when they're learning this, need to do this in 2 steps. So I'll just move the du, and then I don't want this m with the du, so I'll divide by the m. And now what I have is something that has only m's on this side and only u's on this side. All right. So what I do now is I whack some integral signs in. Like that. So the integral of m is ln, the integral of 1 over m is ln the absolute value of m. And the integral of 3, because there's only u's involved here, is 3u plus a constant. Now, you might think that when I'm doing an integral I need a plus c on both sides. You don't, because they're actually different c's. This might be c1 and this is c2. And if it was this, I'm just going to pop it here. If you did do this, like that, you could always do this. And that itself is a constant as well. And so you just end up with this. So you only need to add the plus c on one side. You don't need it on both. Okay. Now the goal is to get m equals. And so I need to keep going until I get there. So if I want to get rid of an ln, what I need to do is e to the power of. And this is a very important point here. Whenever you do an operation on both sides, you have to do it to the thing as a whole. So I can't do e to the 3u and just leave the plus c on the end. And I can't do e to the 3u plus e to the c. That's not how e to the power of works. You have to do e to the power of this and then decide what to do. Okay, so absolute value is either plus or minus depending on whether it's positive or negative. And so I'm going to get this. So what you would usually do is you would use your m of 0 to tell you whether it was the plus or the minus. So in this case, since m of 0 is 8, I know it has to be the plus, because otherwise it would be negative. But even better, I don't even need to do that at all. I can do this extremely cool trick. So if there's a plus here, plus up here in the power is the same as multiplication down below. And all of that is a constant. It's not both plus and minus, it's just one or the other. And so whichever one it is, it's still a constant. And so they normally call this like A. For some A. Now I should tell you that your lecturer has explicitly said in those lecture notes that if you see something of this form, you're allowed to skip straight to this answer without doing the intervening working. I'm actually going to write that explicitly on the next page. But your lecturer has explicitly said in the notes that that's a format you're allowed to just say, just a second, we can do a shortcut, we know how it's going to work out, it's just going to work out to this. Okay? But what I wanted to do was show you that it's really a separable equation. Okay, so we're nearly there. This is a general solution because all different A's are going to work. So now I need to find, there's one piece of information that I haven't used yet. I haven't used this bit of information, so I'm going to use that. But m of 0 is 8. So that means that so m of 0 is a e to the 3 times 0, which is a, because e to the 0 is 1. And so that is supposed to be 8, so the a is 8. So therefore, m is actually 8 e to the 3u. Right. So just note, this gives us a shortcut. This will always happen. If you see something that is dy or d whatever on d whatever, and it's a multiple of y, importantly, this is not x, it's y. If you see that, you're allowed to skip straight to y equals a e to the key kx. Or if it was p and t, you would have p equals a to e to the kt, and so on. Okay? It's a shortcut, but if you can't remember it and you know how to do separable, you can always figure it out. And mostly this is in situations called exponential growth or exponential decay. And the idea that's going on is that the derivative, dy and dx, is some multiple of what the current value is. So if you have a population of, say, bacteria, you've got bacteria germs, and they're growing. If each bacteria separates into 2 bacteria every hour, that means that every hour it will double. And actually, the amount that it changes by, every hour, the amount it changes by is whatever it is right now. Because whatever it is, if there's 2 million of them, then every 2 million of them creates another 2 million, and so the amount it changes by is what it is now. But some things grow a bit slower or grow a bit faster than that, and so it may be that only half of them divide, and so whatever the change is half of what you've got right now. And the other idea is that they do it in physics, as you say, with like the uranium or something, the half-life of things. And so because these processes require an amount of stuff to work, if there's more stuff, they happen faster. But if there's less stuff, they happen slower. And with animals and people, if there's more people, then there are more people to have children, and therefore there you get more children. And so the speed at which things change is based on how big things are right now. And that's how it works. So I don't know if that helps, but sometimes it's useful to think about it in that sort of logical way rather than thinking about it totally in terms of the formulas. Okay, so let's just do another one. What time are we up to? Not too bad. Okay, so let's do another one that's a bit more complicated. Give me a second. No, just wait, don't write it down yet. Right. I'm doing this one. At the moment, this does not look like a separable equation. But you've only been given a couple of methods, so if you saw something like this in the exam and you were told to solve it, it's a pretty safe bet that it's separable. Now, if you were in a different course, you might think, oh, it's one of these other types that you might want to do. But separable is the easiest one anyway. And it's certainly not a basic one because there's a t floating around, there's an x floating around here. And then look, x is actually not, I call this the dependent variable and the independent variable. X isn't the one on the bottom at the moment, it's the one on the top. So we're actually going to get a formula x equals something involving t. So just make sure you keep track of which one's where. So just trying to say, we know the goal is x is function of t because of the way it's currently written. Okay. This is such a physics thing to do, where x is your position on a line and t is time. Okay. So, I'm going to rearrange it. I'm going to remove this x, because I know that the standard version of a separable equation has the derivative all by itself and everything else on the other side. So I'm just going to arrange it to look like that just to make sure I know what's going on. But even now at this stage I can tell it's separable because from this point forward I will be able to move all the x's onto this side with division and all the t's onto that side with division. And as long as I'm using division and multiplication it will be okay. But I'll do it first this way. So now I know it's separable because it's dx and dt equals something involving x divided by something involving t. And it doesn't really matter whether one's divided by the other or multiplied, it'll work. So it'll be a little easier to do the maths here if I literally separate this into two pieces and write this as like that. So something divided by t is the same as multiplying by 1 over t. And so now I can divide by this and multiply by the dt. So I did two things at once there. I divided by the 1 minus x, which is the same as doing multiplying by 1 over 1 minus x, and I multiplied by the dt, so that ended up over here. So two things at once happened there. And now I have managed to create something with x's and dx's on one side and something with t's and dt's on the other, and so now I can integrate them. Most people actually don't write this as a separate line and they just whack the integral signs in. That's okay as well. So yeah, a lot of people when they do this don't include this bit there. They remove that line. They write the thing and then they whack the integral signs in. But I like to write them separately because then I can see what's going on. But in an exam it could save you precious seconds. So okay. So, let's see. The integral of this would be ln of 1 minus x, but that would only be true if this was x, right? If it was 1 over x, it would become ln x. But the thing that's there, its derivative is negative 1. And so when the derivative is a constant, you have to divide by that constant. So if it had been 1 minus 2x, I would have divided by minus 2. If it had been 1 plus 3x, I would have divided by 3. But because it's 1 minus x, I divide by the minus 1. Most people forget to do that, so that's why I'm being very careful about saying what I'm doing. Well, that's distressing. All right. So I've multiplied by the negative 1 to make it go away. And the goal is to get x equals, so, all right, I'll do e to the power of both sides. I'm not liking it, but we're getting there. So we can do that A trick again. Okay. I mean, see that E and that ln are so close together. If they were right next to each other, they'd cancel out. So I really need to deal with that minus. Because e to the negative something is the same as 1 over e to the positive something. And now the e to the power of has an ln inside it and they cancel each other out. A over the absolute value of t. And so now I need to get x equals okay, so x is equal to 1 minus a over the absolute value of t. Fabulous. It's wow. So if t was only allowed to be positive, because if it was time, t would be starting at 0 and moving forward, then the absolute value wouldn't be important because it would always be positive. But I don't know, so I'm just going to have to leave it as it is. So there are quite a few rather nice little algebra tricks going on there. And one of the things that it's useful to know about is if you have an e to the minus ln, if you write it as 1 over, then the e and the ln can cancel. And that's a useful little trick. One of the things I find interesting about calculus is that often it's the algebra that's the hardest bit. Actually, just let me leave that there for a minute while I decide if I'm going to do another example. So the only other example is that when they give you a word problem and you have to turn it into one of these things. And so I might as well give you one of those. I wonder if I can make it financy sounding. Probably not. I could make it marketing sounding. As 1 million, let's do 12 users in January and 10 million in March. If it keeps losing users at a, via an exponential decay, at the same exponential rate, how many users have by July? That's a good question. I like this question. It's very marketing-y. There's too many examples in these courses that are financy. I kind of like having marketing ones. I mean, it's really not marketing, but I'm just pretending that it is. When I did this same thing over in the straight maths course, I think I did it with... so I can't even remember just yesterday. Do 3 revision seminars a day, your brain is just mush. Okay, so when you solve one of these, you need to tell the reader what your letters stand for. So let U be the number of users. Just a second. UT of users at time t measured in months since January. So I've been very specific about what both my variables are. U is the number of users. I've tried to use a letter that makes sense in context. T is time, where T is the number of months since January. If I'd been particularly, I could have used M for months, but T feels like time. Okay, and I've told what the T is measured in. Okay, so January would be T equals 0, i.e. January is T equals 0, and so U of 0 is 12 million. Oh, let's do it in number of users in millions, right? Yeah. So that we don't have to do it actually as 12 million, we can just write it as 12. And March is T equals 2, so U of 2 is 10 million. So we get to choose our own variables, so we can make it simpler for ourselves. And July, February, March, April, May, June, July is 6. And what we would like to know is, what is U of 6? Okay, so we've managed to turn our problem into a maths problem at the moment, but what we haven't done is created a formula that relates U to T. But we know this is exponential growth, or decay in this case. So technically it's a differential equation. All right, so if you're losing the same percentage each month, so this is my guess. My guess is we're losing 2/12, so a sixth of the customers each month. And so in 2 months, sorry. In 2 months we lose a sixth of the customers. So in March, April, May, in May we should have 1/6 less than 10 million. So we should be down to whatever that is, 5/6 of 10. And then the next 2 months we should lose a sixth of what we had so far. So I can probably do this without even using any of this stuff and just do it as in sixths like that. But we're going to do it properly. So the idea is that if we want to do it as a differential equation, it'll be some multiple of how many users we have so far, you know, like 80% of the number of users we have at the moment, right? That's the idea. The change that we have, oh no, not 80%. The change is like minus 20%. That's the idea. And we know that that's going to get us to this. Because we're allowed to just skip to that. Okay. So we have 2 pieces of information about the numbers, and so we can use 2 pieces of information to figure out two missing letters. So we know that U of 0 is A e to the k times 0, which is A, and that's supposed to be 12, and so that's great. We know what A is. So therefore U is actually 12 e to the kt. And we know that U of 2 is A e to the, 12, we know what, 12 e to the k times 2, and that's supposed to work out to 10. And so e to the k times 2 is 10/12. Which is the thing I figured out just before, which is 5/6. Actually, I'm not going to put it there because I need to use it in a minute. And so I could, if I wanted to, figure out what k was, if I wanted. So I could do this. I could go, Well, if I do ln on both sides, then ln of e to the something, they cancel each other out. And then I would get that k is whatever this is. And you could figure out that with a calculator and see what it works out to be. I didn't bring a calculator, so I will use Desmos. Half of ln of 5, 6. Yeah, k times 2, sorry. I really should have written it as 2k, but, you know, I was in the groove. So it's k times 2 here because the 2 is in the position the t was, right? So I matched them up, but then I should have written it as 2k, but I didn't. 0.091 approximately. So what this is telling me is that on average we're losing about 9% a month. That's what this is saying. So no, on average. That's why you might want to know the k, so that you can do that. I mean, in continuous compounding or whatever, it would be that number. But we don't actually technically need to know what k is to actually solve this problem. It's not actually necessary. And I'm going to actually show you. So this is great, this bit of working, but we don't actually need it unless someone asks, because I only need to know what e to the power of k is. This is a cool trick I want to show you. So back at this stage, if I do both sides to the power of a half, then when you do powers of powers, you multiply the powers. And I have e to the k times 2 times a half, so it will be e to the power of k equals this. Okay? So the square root of that, basically. And now, nothing up my sleeves, e to the k to the power of t that means that e to the kt is 5/6 to the half of t, which I think is awesome, because that means that now u of t is 12 e to the kt, which is now 12 times 5/6 to the half of t, and I don't need k. It's all in terms of powers instead, which I think is awesome. Means I don't have any round off error when I put it in my calculator. Yeah?
The fourth one from the bottom, is that e to the power of k to the power of t?
Yep, sorry. Wow, the light changes when I put my hand on there. That's weird. Okay, and so what was the actual goal? What is it at t equals 6? So we want u of 6, which is 12 times 5/6 to the half times 6, which is 12 times 5/6 cubed, which I would ask my calculator for. .94 to 2 decimal places. So in July, there are, 6.94 million users left. If they don't do anything, right, if they don't put in some sort of campaign to try and get their users back, or apologise for some sort of crap they did. Okay, so I just want to point out something. I already said that this is what the answer would be. We had 10/12 of what we had before in 2 months. So in another 2 months we'll have so that's 5/6 of what we had before, and in another 2 months we'll times by another 5/6, and in another 2 months we'll times by another 5/6. That's exactly what this says, which I think is awesome. So if you didn't have time to do all the proper way, you could just argue that out, and it would be fine. So I don't know how many marks you'd get, but you'd certainly have the right final answer, so you'd get something. Yes? Where? Oh, it stands for 2 decimal places. Because it's not technically actually equal to this. It's like 6.944444444. So I'm used to telling people how many decimal places I've rounded off to. Yeah. Well, I think that's quite enough differential equations, especially because, especially because we've got about a minute to go. Yeah. But I'm feeling in a good mood, so we may be able to, if there's something short, to do one of these things. Yep?
I've got another suggestion.
Yep.
Something if there's nothing else. It's a probability question.
Okay. How do people feel about just doing a probability question from one? Is this from one of the practice exams? So I probably don't have enough time to talk about this. I have talked about in past revision seminars, so it should be there. And I'm pretty sure I've done a Lagrange multiplier, and they don't have time for that. That's not enough time for that. There are already revision seminars on pretty much all of these things already. On the AQMF page, so when I sent the email about this, there's a link there, and there's revision seminars there already. So let me show you just a second. I could spell it right, couldn't I? So these are all the past revision seminars. So
can we bring in a computer cheat sheet, like a printed cheat sheet?
you will have to check the rules. That is, I am not part of the people who run this course, so I can't tell you what you're allowed to bring into your exam or not.
Typically for maths, is it fine?
Sorry?
Is it fine to...
Years ago they said must be handwritten, but I remember having a conversation with the coordinator of first year maths and I thought I had convinced them that it was okay to bring a printed one, but I can't remember.
What's the thinking behind not allowing a printed one?
People think that it's better, there is research to suggest that you remember things better if you write them with your own hand, but then the point of a cheat sheet is to have the things you can't remember. So it's a bit paradoxical. The research suggests that cheat sheets don't help very much other than to make you feel better. Like, they're a useful thing to help make sense of your study, and they stop you freaking out at accidentally forgetting something, and so less stress makes you better in the exam. But overall, they don't do much for people's grades, but a little bit because you feel better. And so my argument is, if the whole point of a cheat sheet is to make you feel better, then let people do whatever they want. So that's what I tried to argue to them, but I don't know how they go. In the past you were allowed to bring printed ones, so you're just going to have to check, and it should be somewhere in my uni, and if it's not, ask someone involved in your course. Yeah. Okay, so this is what I've got. I will probably just add it to the list. I'll put it at the bottom, Revisions Seminar 2019, the one from this year. And you'll notice they're sort of roughly in order of time. Okay. Or maybe I don't have a Lagrange one. Oh yes, I've got one with Lagrange multipliers, so that's good. Okay, tell me this question. No, it's all good. Okay. All right. So I'm just going to leave it there. I think we did a pretty comprehensive job of the differential equations, actually. How do you feel? Yeah, because you were the one who wrote it, so I was just checking. Okay. All right. I'm going to stop because I should probably rest before the next one. Thanks very much for coming. Don't forget the Maths Learning Centre is open for the entire exam period, including, if this is relevant to you, next Monday, which is cutting it a bit fine, but you never know. Yeah, I personally won't be there until tomorrow afternoon because I've still got revision seminars, but I will be there the rest of the time. And yeah, good luck.